Good morning, students. Today we are going to discuss about alkanes. This is the subtopic of the second topic in the second unit of organic chemistry, that is acyclic hydrocarbons. In acyclic hydrocarbons, we are going to discuss about alkanes, alkenes, and alkynes. So today we are going to discuss about alkanes. So what are alkanes? Alkanes are saturated hydrocarbons that contain only carbon, hydrogen, and a single bond. In between carbon and hydrogen, single bond is present, and in between carbon and carbon also single bonds are present. Then they are called saturated hydrocarbons. Hydrocarbons in the sense the compounds containing carbon and hydrogen exclusively, and saturated in the sense in between carbon and carbon only single bonds are present. Anyhow, carbon in between carbon and hydrogen single bond will be present. So the hydrocarbons not having pi bonds, that is double and triple bonds, are called saturated hydrocarbons. So in alkanes, carbon is sp3 hybridized and there is no reactive functional group. Because of that reason only, alkanes are less reactive as they do not have any reactive functional group. And here, although alkanes undergo reactions such as combustion and cracking at high temperatures, they are much less reactive and than other classes of organic compounds having functional groups, as there is no particular functional group in alkanes. Alkanes are found widely in nature. They are the major constants of natural gas used to heat homes and gasoline used as fuel in automobiles. Now, the general formula of alkanes is CnH2n plus 2 and alkyl group is CnH2n plus 1. So, where n is an integer, here alkane, let us consider when n is equal to 1, C1H2 1 plus 2, that is CH4. This is the first member of alkane series, and when n is equal to 2, C2H2 plus 2, that is C2H2 into 2 to n is equal to, therefore 2 into 2 plus 2. Therefore, it is C2H6. Now, if we consider the alkyl group obtained from this methane, N equals to 1, the alkyl group general formula is CnH2n plus 1, Cn C1, H2 into 1 is 2 plus 1 is 3. So, CH3 dash, this is methyl group obtained from methane. And thus, when N is equal to 2, we get C2H5. This is ethyl group obtained from C2H6 by the loss of one hydrogen atom. Now, let's see the nomenclature and the preparations of alkanes. The IUPAC name of alkanes has three parts. One is prefix, then parent, then suffix. Prefix, parent, and suffix. Now, first of all, alkanes are named using the Greek word for the number of carbon atoms plus the suffix "ane" to identify the molecule of an alkane. So, root word first of all, we should consider the root word based on the number of carbon atoms, and to that a suffix "ane" is added. Now, if number of carbon atoms equal to 1, then the parent name or the root word used is meth. If it is 2, it is eth, and if it is 3, it is prop, and if it is 4, the parent name given is but, 5 pent, 6 is hex, 7 hept, 8 oct, 9 is non, and 10 is dec. So these are the root words or parent name given to alkanes based on the number of carbon atoms. And to this, the suffix "ane" is added to complete the name of the alkane. So RH is called an alkane. This is the general formula given to alkane RH. Then R is called an alkyl group. Okay. Now, let us see some popular alkyl radicals here. So this is methyl radical CH3 dash. This is CH3 CH2 or C2H5 dash ethyl radical. This is N propyl radical. And this is CH3 CH2 CH2 dash, that is N propyl radical. And this is isopropyl radical CH3 CH dash and CH3 isopropyl radical. Similarly, N butyl, secondary butyl, tertiary butyl, isobutyl, and this is neopentyl radicals. These are the different radicals obtained from alkanes. Now, let us see the some alkanes. Here N-butane we considered. N stands for normal, normal in the sense no branching, and but because of four carbon atoms. N is the general suffix for alkanes. So it is N-butane. This is isobutane. Four carbon atoms are there, a fork shape. Because of that reason, it is called iso. But means four carbons, N means all are single bonds or alkane. So this is another example given. These are the two different examples for alkanes. Now let us see the preparations of alkanes. Preparations. There are four different important preparations of alkanes. The first one is from Grignard's reagent. Second one is Wood's reaction. Third one is Kolbe's electrolytic method or Kolbe's electrolysis. And next one is Corey-House reaction. By these four methods, we can prepare alkanes. Now let us see one by one in detail. First one is from Grignard's reagents. So how do we prepare alkanes from Grignard's reagents? Alkyl magnesium halide is called Grignard's reagent and it is denoted by the formula RMgX. Alkyl magnesium halides are called Grignard's reagents, denoted by the formula RMgX. So, when this alkyl magnesium halide is decomposed to alkane on treatment with water or dilute acid or any other compound having active hydrogen. Okay, active hydrogen in the sense the hydrogen which is attached to oxygen, nitrogen, fluorine or triple bonded carbon. So their active hydrogen is present. So when alkyl magnesium halide is decomposed to alkane by the treatment of either water or dilute acid or any other compound having active hydrogen. Now let us see the reaction. RMGX, when it is subjected to hydrolysis, that is decomposed with the water, then what happens here? The bond breaks here, and R goes with H and the rest of the part goes with OH. Then we will get this product, that is RH is nothing but alkane and the other one is hydroxy magnesium halide. Hydroxy magnesium halide. So OH of water goes with this part and H of water goes with this part of RMGX. Then we get alkane plus hydroxy magnesium halide. This is with water. And if it is ammonia, then H goes with the R and the rest of the NH2. That is rest of the part of this ammonia goes with the MgX. Then we will get this molecule. So here when a specific example if we consider, this is ethyl magnesium bromide. This is an example for alkyl magnesium halide, that is Grignard's reagent. So ethyl magnesium bromide, when it is treated with water, when it is decomposed with water, let me say, then what happens? The bond breaks here. Hydrogen of this HOH goes with this ethyl group, then we will get ethane CH3 and OH goes with this rest of the part, that is MgOHBr, that is hydroxy magnesium bromide. So in this method we can prepare alkanes. So this is one best method for the preparation of alkanes from Grignard's reagents. Okay. Now let's see the next method of preparation. Method of preparation of alkanes. That is Wood's reaction. It is very important reaction. Wood's reaction is one of the oldest reactions used to couple two alkyl halides. Generally, bromides or iodides to form an alkane in presence of sodium metal in dry ether medium. So, sodium metal and dry ether. So alkyl halide, this is RX is the general formula of alkyl halide. Two molecules of let me say alkyl halide treated with sodium metal in presence of dry ether solvent. Then what happens? We will get higher alkane or higher alkane and this is sodium halide. Now let's discuss the mechanism of this Woods reaction. So the two mechanisms are proposed for this reaction. Two mechanisms are proposed for this reaction. Uh, There, the first one, let us see the intermediate formation of an organometallic compound. This is one method, and the second one is the intermediate formation of free radicals. So, in these two ways, higher alkane is obtained from alkyl halide in presence of sodium metal. So, let's discuss about the two different mechanisms one by one. So, first one, intermediate metallic compound, intermediate formation of an organometallic compound. So here alkyl halide reacts with sodium metal to form, this is an organometallic compound, this is organic part and this is metal, so organometallic compound RNA. So this is obtained. In the next step, what happens? This organometallic compound, it combines with another molecule of RX, another molecule of RX to form R and R, that is alkane, and NaX. This is sodium halide. Sodium halide. Okay, so in this way, in an intermediate of organometallic compound is formed, which reacts with another molecule of alkyl halide to form an alkane. So this is one mechanism in which alkane is obtained in Woods reaction. Now, second mechanism, let us consider. It is the intermediate formation of free radicals. So, first of all, let us consider one alkyl halide molecule. One alkyl halide molecule. This molecule, when it is treated with the sodium free radical, then what happens? The sodium free radical, it combines with the X free radical, that is halogen atom. Sodium atom combines with halogen atom to form NaX, leaving behind alkyl free radical. So this homolytic bond fission of this bond takes place, then R dot and X dot we get. This X dot, it combines with sodium atom to form sodium halide. And here this in this way, this alkyl free radical, it combines with another alkyl free radical to form the alkane. So this is the intermediate formation of free radicals. So here the intermediate produced in this reaction mechanism is a free radical. In the previous method, the intermediate produced is organometallic compound. So in these two methods, two ways, in one method, intermediate formation of organometallic compound, and the next method, intermediate formation of free radicals. So, in these two ways, we can explain the mechanism of Woods reaction. So, in Woods reaction, what happens? Alkyl halides, they react with sodium metal in presence of dry ether to form higher alkanes. So, this is the two mechanisms for uh, Woods reaction. And here, let's discuss an example. Generally, Woods reaction forms symmetrical alkane having an even number of carbon atoms. In the Woods reaction, only we will get the alkanes with even number of carbon atoms. Even number of carbon atoms. Let us discuss this with an example. Let's consider methyl halide here. Methyl CH3X methyl halide. If we HCl, methyl chloride we can say. Okay, when this two molecules of this methyl halide treated with sodium metal in presence of dry ether, we get ethane. So when in this reaction, we got an alkane having two carbon atoms, and this is sodium halide. But if two different alkyl halides are taken, then all possible alkanes are formed. Only same alkane is here symmetrical alkanes we consider, we get the that is an alkane having even number of carbon atoms. That is, symmetrical alkane is produced when we consider only one type of alkyl halide in the Woods reaction. If we consider two different types of alkyl halides in the Woods reaction, we get a mixture of alkanes. But the separation of this mixture is difficult. Because of that reason, we can say that in Woods reaction, preparation of uh, uh, alkanes with odd number of carbon atoms is difficult. So here, for this, let us discuss one example. Here methyl halide one molecule, and we considered one molecule of ethyl halide. When treated with sodium metal in presence of dry ether, we get ethane. That is, if these two molecules, if they combine, we will get ethane. If these two molecules, if they combine, we get n-butane, 4 carbon alkane. And if this and this one molecule of this, one molecule of this, if they combine, we get propane. Like this, we get the mixture of the compound, and mixture separation is difficult. Because of that reason, we say that synthesis of alkanes having odd number of carbon atoms in Woods reaction is difficult. And at the same time, we cannot prepare methane with the help of Woods reaction. This is also important point we should remember. Okay. Now, next method of preparation of alkanes is coal-based electrolytic method. Coal-based electrolytic method. In coal-based electrolytic method, the coal-based electrolysis, we say. This is an electrochemical decarboxylative dimerization. Dimerization takes place, and decarboxylation means loss, carboxylation means CO2. Loss of CO2 also takes place in this reaction. So this is an electrochemical reaction, that is, it takes place in presence of electricity. Because of that reason, it is called coal-based electrolysis. So this is the electrochemical decarboxylative dimerization of carboxylic acid salt, that is salts of carboxylic acid, leading to the formation of alkanes. So this reaction is known as coal-based reaction. So coal-based reaction is a decarboxylative dimerization of salts of carboxylic acids in presence of electricity. This point we should remember. Okay. Now let us consider the salt of carboxylic acid here. Potassium salt of carboxylic acid, either sodium or potassium salt of carboxylic acid. So we can consider. Here we considered potassium salt of carboxylic acid, RCOOK. This is potassium carboxylate. Aqueous solution we considered. Aqueous solution of this potassium salt of carboxylic acid. Aqueous solution we considered. This is subjected to electrolysis. So electricity is passed. Then what happens? We get alkane and hydrogen plus 2 moles of KOH and 2 moles of CO2. So this CO2, 2 moles, R and R is alkane, and from this HOH, that is H2O, H2 we get, and OH goes with K in the form of KOH. So this is the reaction. So here what happens? The bond breaks here. This anyhow this is ionized. Uh, it is in the form of ions because it is salt of the carboxylic acid. Now let's consider the mechanism. At anode, what happens? This carboxylate ion, it loses an electron to form carboxylate free radical. Free radical having an unpaired electron or odd electron. Carboxylate free radical is produced from the carboxylate ion by the loss of an electron. At anode, loss of electrons takes place, that is oxidation. So next in at anode, then when this carboxylate ion is carboxylate free radical is produced, this combines with this decomposes to form CO2 and alkyl free radical. This one, it loses carboxylate free radical, loses CO2 to form alkyl free radical, and two alkyl free radicals, they combine to form an alkane. This is what taking place at anode. So the gas released at anode is carbon dioxide. This we should remember. And next one, at cathode, what happens? At cathode, the sodium ions are potassium ions. Here potassium ions, let us say. So potassium ions are sodium ions, because here we considered either potassium or sodium salt. So if sodium ions are there, sodium, or potassium ions are potassium. So potassium ions They react with this water molecule, water molecule, it, and it gains the electrons lost by the carboxylate ion at anode to form sodium hydroxide and hydrogen gas. So the gas released at cathode is hydrogen, the gas released at anode is carbon dioxide. And these are the products obtained. So in this reaction, alkane and H2 are obtained. Alkane and CO2 are obtained at anode, and H2 and KOH are KOH is produced in the solution, no problem, and H2 gas is obtained at cathode. So this is what we should remember. This is Kolbe's electrolytic method. So in Kolbe's electrolytic method, sodium or potassium salt of carboxylic acid aqueous solution is subjected to electrolysis. Then alkane and CO2 are obtained at anode, and hydrogen gas is produced at cathode along with the base like NaOH or KOH. This is one more important preparation. Next preparation of alkanes is Corey-House reaction. So Corey-House reaction. So this is one of the advanced method for the preparation of higher alkanes. To prepare higher alkanes, this is the best method or advanced method, recent method, let me say. So it involves nucleophilic substitution of halo compounds with lithium diorganocuprate. Lithium diorganocuprate is considered, and here what is that happening? Nucleophilic substitution of halo compounds with lithium diorganocuprate. Okay, now let us consider the example here. So Rx is alkyl halide, where X is chlorine bromine iodine, and this is treated with this one, dialkyl lithium cuprate. So dialkyl, here dialkyl cuprate, this is, so lithium dialkyl cuprate we considered, and this when this is treated with alkyl halide, we get an alkane, higher alkane, R and R higher alkane is obtained, plus RCU. RCU, this is an organometallic compound, plus lithium halide. So Li with the X, lithium halide, R and Cu, RCU, and this R and this R combines to form this alkene. So higher alkane is obtained. So reactivity of halo compounds is in the order of this alkyl halides is in the order of primary greater than secondary greater than tertiary. So primary alkyl halide is more reactive in this reaction when compared to secondary, which is more reactive when compared to tertiary alkyl halide. So this is reactivity order of alkyl halides in Corey-House reaction. So specific example here we have given, this is N-butyl bromide, that is Rx, this one, plus this is uh, lithium dimethyl cuprate, lithium dimethyl cuprate, this we considered. Then the product obtained is R and R. So this is 4 carbon alkyl group, and this is 1 carbon alkyl group. So altogether 4 plus 1 5. So pentane is obtained in this reaction. So this is about Corey-House reaction. It is the advanced method for the preparation of higher alkanes, we said. So next, chemical reactivity of alkanes. So what are the chemical properties of alkanes? How alkanes are converted into alkyl halides. That one we will discuss in chemical reactivity. So alkanes do not have any reactive functional group, thus they are chemically inert. We have already stated in alkanes only carbon and hydrogens are present. No specific, no special functional group is present. Because of that reason, alkanes are chemically inert, or they are less reactive. They are not attacked by acids, bases, oxidizing or reducing agents at ordinary temperature. So they do not react with acids, bases or oxidizing agents and reducing agents at ordinary temperatures, because they are chemically inert due to absence of a functional group. Now, halogenation of alkanes are free radical substitution. Halogenation of alkanes is a free radical substitution reaction, which we have already discussed in the previous section about the uh, types of organic reactions. There we studied about addition reactions, substitution reactions. And there in substitution reactions there are three types we said: electrophilic substitution, nucleophilic substitution, and free radical substitution reactions. So here this halogenation of alkanes is a free radical substitution reaction. Okay, so alkanes generally they undergo free radical substitution with halogens in presence of light and produce a mixture of products. A mixture of products are produced. So the halogen molecule dissociates into free radicals initially, and these free radicals attack on alkane and abstract hydrogen molecule from any part of the alkane molecule and produce a mixture of products. So this is what happens in the halogenation of alkanes, where it is a free radical substitution reaction. So in the free radical substitution reaction, what reaction it takes place in presence of light, that is generally ultraviolet light, to produce a mixture of products. So initially what happens, halogen molecule dissociates into free radicals, and then this free radical it abstracts um, a hydrogen atom from any part of the alkane to form the alkyl halide mixture of alkyl halides, let me say. Okay, now let's see the reaction here. This is R and H, it should be H, not X. Okay, RH is alkane. When treated with the X2, that is halogen, in presence of light, that is ultraviolet light, or heating to 250 to 400 degrees centigrade, then what happens here, H is replaced by X and we will get RX and HX. So it should be H. Okay, this is RH is alkane, it should be H. So here this H is replaced, substituted by halogen atom. Then we will get Rx, that is alkyl halide, and HX. So this is the reaction, which is a free radical substitution reaction. Now in this reaction the reactivity order of X2 is fluorine is greater than chlorine, which is greater than bromine, which is greater than iodine. So here if we take fluorine, the reaction is faster, we mean to say. So the reactivity is more: fluorine, chlorine, bromine, and iodine. But the reactivity order of RH, is that is R group, we mean to say. RH is tertiary is greater than secondary, which is greater than primary, which is greater than methyl. Okay, so this is about the methyl and H. R and H, we said RH, that is alkane, methane. So tertiary is greater than secondary, which is greater than primary, which is greater than methyl group, or methane. So under the influence of light, that is UV light, at 250 to 400 degrees centigrade, chlorination and bromination takes place. And direct fluorination is explosive reaction, and iodination is reversible reaction. So generally we consider chlorination and bromination reactions of alkenes in this method. Okay, now let's see this. Depending on position of substitution, all possible isomeric products are formed in unequal amounts. Equal amounts of the products are not produced. In unequal amounts, the different products are produced based on the position of the substitution. So let us consider ethane. If we consider ethane, when it is treated with chlorine in presence of light, then we will get ethyl chloride. If it is propane, it is treated with chlorine in presence of sunlight, we will get two different products, because based on the position of the substitution. If this chlorine atom, if it substitutes hydrogen from this carbon or this carbon, we will get this compound, that is 1-chloropropane. Whereas if this chlorine goes and substitute one of the hydrogen atoms on the second carbon, then what happens, we will get this product, that is 2-chloropropane. Here the uh, So in this reaction, 45% of 1-chloropropane and 55% of 2-chloropropane are obtained. Okay. Now, if we consider this one, this is isobutane or 2-methyl propane. When this is treated with chlorine in presence of sunlight, then we will get 64% of this compound, where chlorine atom displaces hydrogen atom from either this or this or this, all are equal carbon. Then we will get this compound. Okay, and if it abstracts the proton from this, that is hydrogen atom, from the middle carbon atom, we will get this compound. So the amount of first compound is 64% and this compound is 36%. Now, if we consider bromination reaction. In the bromination reaction, ethane, when treated with bromine in presence of HNO, that is light, are heating to 250 to 400 degrees centigrade, we will get ethyl bromide. If it is propane and bromination, we will get 1 bromopropane 3% and 97% of 2 bromopropane. In the previous reaction, in the chlorination reaction, you can see 1 chloropropane 45%, 2 chloro 55%. Whereas in the bromination reaction, 1 bromopropane 3% and 2 bromopropane 97%. This in a similar way, in the second reaction, similar to this one, bromination of isobutane, 1% of this compound and 99% of this compound is obtained. You can see the difference here. Okay, so now why this is happening, that we will discuss in the selectivity. So mechanism, first of all, mechanism of halogenation. Let us see mechanism of halogenation of alkanes. In the first step, this mechanism involves three steps, and it is a chain reaction. The first step is known as chain initiation step, where this halogen, in presence of the sunlight or UV light, it decomposes to give halogen free radicals. So X2 gives rise to 2X dot. So two halogen free radicals are produced. And the second step, that is chain propagation step, there what happens, this halogen free radical, it abstracts hydrogen atom or hydrogen free radical from RH to give alkyl free radical and HX. In the same chain propagation, in the next reaction, this alkyl free radical which is produced, it combines with one more molecule of X2, that is halogen, to form RX, that is alkyl halide, and giving X dot, that is halogen free radical. Halogen free radical. These two reactions, that is reaction 2 and 3, are repeatedly taking place to propagate the chain. To propagate the chain, producing alkyl halides and halogen free radicals. And this reaction stops, that is termination of the chain reaction takes place due to any of these three reactions. The first reaction is two halogen free radicals. If they combine to form X2, the reaction stops. This next one is two alkyl free radicals. If they combine to form an alkane, then also the reaction stops. The chain reaction stops. Or in the other words, if this alkyl free radical, if it combines with this halogen free radical, then also the reaction stops by forming an alkyl halide. So these are the three steps involved in the halogenation of alkanes. First one is chain initiation step, where alkyl free the halogen free radical is obtained. And the second step, that is chain propagation step. In the chain propagation, there are two reactions. In the first reaction, alkyl free radical is obtained. In the second reaction, alkyl halide and halogen free radicals are obtained. These two reactions continuously take place, propagating the chain reaction. And finally, the chain termination reaction, where there are three different reactions. Any one can take place to stop the chain reaction. The first one is two halogen free radicals combine to form halogen molecule, or two alkyl free radicals combine to form alkane molecule are two are one alkyl free radical and halogen free radical combines to form an alkyl halide. So in this way chain termination takes place. Now here step 2, that is chain propagation step, is more difficult than step 3 and hence controls the rate of the overall reaction. So the alkyl free radical formed is readily converted into the alkyl halide, converted into CON, converted into the alkyl halide. So next one is orientation of halogenation. Orientation of halogenation. In the orientation of halogenation, what we are going to discuss is if an alkane is having more than one reactive sites to be attacked by the reagent, the orientation determines the formation of the major product. In the previous slide, we discussed about the chlorination and bromination of propane and isobutane. There we got different quantities of various products. Why this is happening, that we can discuss based on this orientation and selectivity. So if an alkane is having more than one reactive sites to be attacked by a reagent, the orientation determines the formation of the major product. Okay, so the stability of alkyl free radicals mainly controls the orientation. So, which alkyl free radical is more stable? Based on that, which compound is formed, we can explain. Okay, so the order of ease of substitution is tertiary is greater than secondary, which is greater than primary, as the general stability order of alkyl radicals is this one. So, general stability of alkyl radicals, we have already discussed that a tertiary alkyl radical is more stable than secondary, which is more stable than primary. So, because of that reason, the ease of substitution is also in the same order, that is tertiary is greater than secondary, which is greater than primary. That is tertiary alkyl halide is easily formed when compared to secondary, which is easily formed when compared to primary. This we can explain based on the orientation of halogenation. Let's consider this reaction. This is propane CH3 CH2 CH3. Okay, so this two hydrogens we separately shown because we want to show the substitution at these two positions. This is primary carbon, this is secondary carbon. This is primary carbon because it is attached to one other carbon. This is secondary carbon because it is attached to two other carbons. Okay, so this is primary and this is secondary carbon. So when chlorine free radical attacks or abstracts a hydrogen free radical or a hydrogen atom from primary carbon and secondary carbon, what happens? Let us see. In the first one, abstraction of primary hydrogen and hydrogen from this primary carbon, if it is abstracted by this chlorine free radical, what happens? Let us see. Then this H dot is abstracted by this chlorine dot, then we will get CH3, CH2, CH2 dot. See, CH3, CH2, CH2 dot. This is N-propyl free radical. N-propyl, N stands for normal. Normal means no branching. N-propyl or 1-propyl free radical. Okay, this is primary free radical is produced. Okay, this primary free radical, when it is produced in the second stage, that is chain propagation stage, it combines with halogen to form primary alkyl halide, primary propyl chloride. లేదా we can say that this is 1-chloropropane is obtained here in this reaction. Now let us consider the abstraction of the secondary hydrogen by chlorine free radical. Abstraction of secondary hydrogen, that is hydrogen from this carbon by this chlorine free radical. Then what happens? We will get a more stable secondary free radical is obtained. We have already discussed free radical stability. Tertiary is greater than secondary, which is greater than primary. So it is secondary free radical which is more stable. This is primary free radical which is less stable. Therefore, the product of when it is less stable, it is less formed, and therefore this is the minor product. Now it is more stable, it is more amount, it is formed in more amounts, it is formed, then it combines with the chlorine molecule, this free radical, to form 2-chloropropane as a major product. 2-chloropropane as a major product because secondary free radical is more stable than primary free radical. So based on the orientation, we can explain the amount of the substance formed, that is amount of alkyl halide formed in this reaction. Now, the energies of activation for the abstraction of hydrogen atom from various carbons. Okay, so this is like this. RH plus X gives rise to X dot, gives rise to R dot plus HX. For this reaction, X is halogen, that is, if it is chlorine. For methyl, it is energy of activation in kilocalories per mole. It is 4 kilocalories. For primary alkyl halide, it is 1. If it is secondary, 0.5. If it is tertiary, zero point 0.1. Lesser the activation energy, greater is the reactivity. So, activation energy is less here. That indicates that this tertiary alkyl halide is more reactive in the halogenation reaction. So, if it is X is bromine, then the amounts of energy of activations, if for methyl it is 18, for primary alkyl halide it is 13, for secondary it is 10, for tertiary it is 7.5. So from here to here it is decreased. So as the activation energy is less, the reactivity is more. So from methyl to tertiary, the activation energy is decreasing. That indicates that the reactivity is increased. Okay. Now, reactivity and selectivity. Let us see the reactivity and selectivity. In reaction with alkane, the bromine atom is less reactive and more selective than chlorine atom. So bromine is less reactive than chlorine, and as bromine is less reactive, it is more selective than chlorine atom. Now, as the general relationships in groups of similar reactions, the less reactive the reagent, more selective is in its attack. When the reagent is less reactive, it is more selective. So here bromine is less reactive, it is more selective. Chlorine is more reactive, therefore it is less selective. So this point we should remember from this statement. So the reactive site which produces stable radical is more selective. So the reactive site which produces a stable radical is more selective. That is, if we consider bromination and chlorination reactions, bromine is less reactive, therefore it is more selective. That is, it selects the reactive site um, when compared to chlorine. So bromine is less reactive than chlorine, therefore bromination is more selective than chlorination reaction. Let us discuss this taking an example. This is N-butane, CH3, CH2, CH2, CH3. This is N-butane chlorination reaction. Then we get 28% of 1-chlorobutane and 72% of 2-chlorobutane. 2-chlorobutane. This is chlorination reaction. Okay. If we consider the bromination reaction, same N-butane we have considered bromination of N-butane in presence of light. Then we get 2% of 1-bromobutane and 98% of 2-bromobutane. So, as bromine is less reactive, it is more selective. Because of that reason, it forms the more stable product as a major product, that is 2-bromobutane. This is secondary free radical. This is primary free radical produced in the reaction mechanism. So, as it is less reactive, bromine, it is less reactive. It extracts a proton, that is hydrogen free radical from second carbon of butane to form 2-bromobutane as a major product. So here chlorine, it is more reactive. Because of that reason, its selectivity is less. Thus, we got 1-chlorobutane and 2-chlorobutane in this ratio, 28% and 72%. Whereas in bromination reaction, 1-bromobutane is only 2%. That is almost nil, we can say. So, the major product is 100%, almost 100% major product obtained. That is 2-bromobutane, because bromine is less reactive and more selective, and it forms only the stable product. So this we can explain based on the reactivity and selectivity of bromine. Now, what are the different questions we come across in the topic which we have covered today? There, the first one is, why alkenes are reactive in Why alkanes are less reactive. Sorry, this is less reactive in chemical reactions. So as they do not have any functional group, they are less reactive, we should say. Write any two preparations of alkanes. So Corey-House reaction, Woods reaction, from Grignard's reagent, coal-based electrolysis, anyone you can write. What is Woods reaction? Explain with an example. So Woods reaction, or Woods reaction definition and equation and example we should give here. Give the mechanism of photochemical halogenation of alkanes. That is halogenation of alkanes. That is, it is a chain reaction, involves three stages: chain initiation, chain propagation, and chain termination. All that we can explain here. So describe reactivity and selectivity of halogenation of alkanes, choosing a suitable example. So taking butane as an example, bromination and chlorination we can explain easily. So next one is what is a Corey-House reaction? Explain with an example. Corey-House reaction, lithium organocuprate reacts with an alkyl halide to form higher alkanes. This is Corey-House reaction. This is advanced reaction for the preparation of higher alkanes. Like this, we can write the answers. Okay. So these are the important questions we come across from the topic which we have covered today. Okay. So thank you all, and we will continue the next topic of cyclic hydrocarbons, that is alkenes in the next class. Thank you.